Okay, let's continue our discussion for conservation of energy. So we have introduced two important concepts, conservative force and non-conservative force. So if you haven't remember or understand what's that, please try to recall the definition of conservative force and non-conservative force in your head. Now, we are more interested in conservative force now because for conservative force we can associate a special kind of energy to it. We call it potential energy. The work that can be done on objects associated by a conservative force, we can call it potential energy. Now, the definition of potential energy is a negative of work done by a conservative force acting on its path between 2 points. So this is the work. So if you have an object move from point 1 to point 2, now this is the work done by this conservative force moving from 1 to 2, and then you put a negative sign in front, and we call this one change of potential energy. It sounds confusing, but actually it's not. So let's just using gravity as one example. So let's say this is 1 meter, this is 2 meter. Okay, in this case, moving from point 1 to point 2, you have 1 kilogram box. The work done by gravity, you see, gravity is pointing down, displacement is going up. So it's negative work. The work done by gravity is mg, which is a force times displacement 1 meter. So the work done by gravity is 9.8 joules, negative 9.8 joules. So this is the work done by gravity. Work done by gravity. So change of potential energy is negative Wg is positive 9.8 joules, right? So basically that's what it says. The change of potential energy is the negative of the work done by this conservative force. Okay, spring force. We have learned the energy inside a spring because the force, spring force, proportional to displacement. This is kx, this is x, so this area is 1/2 kx squared. And we know if you have force versus displacement or forces versus position graph, the area means work. Now this is the equilibrium position of the spring. You pull it by x, which means you did some work. You did some work to the spring. So the spring will get some energy from the work you did. And the work you did is 1/2 kx squared using this graph we have here. And all the work you've done to the spring becomes elastic energy for the spring, which is also 1/2 kx squared. So you did work 1/2 kx squared, and the spring gets the energy 1/2 kx squared. Okay, you see, hold on. There's a negative there. What's going on? Now the work you did is 1/2 kx squared. For this movement, the work done by spring is negative 1/2 kx squared. That's the work done by spring. And the potential energy of the spring increase is negative of work done by spring, which is 1/2 kx squared. Okay, so don't want to get you confused. Now you can just remember, if a spring is with a displacement x from its equilibrium position, the energy stored inside of the spring is 1/2 kx squared. Doesn't matter this way or this way. So if you press the spring, it's still just 1/2 x squared. Because you see is displacement square, so the direction of displacement doesn't matter. Now gravity. The work done by gravity. Now you have a car climbing this hill, and the work done, if you want to lift this car, you have to do some work. Your force have to be pointing up. Now you have to do work mg delta y to lift this car. On the other hand, see, this is a work done by you to lift this car. So the work is positive if you are going to lift this car up, or the work done by your force would be negative if you to put this car lower. However, the work done by gravity is vice versa. So because gravity is always pointing down, so if you are lifting something, your displacement is up, gravity is doing negative work. Now if you are lowering something, so your displacement and gravity in the same direction. If you lower something, then the work done by gravity is positive. If something raised, then the work done by gravity is negative. Okay. Now this is another illustration. From point initial position to final position, no matter what path you took, the work done by gravity is mg yf subtract yi. If you took this path, it's also mg yf subtract yi. See, any path for gravity, the work done by gravity only depends on the height of initial position and the final position. So we're ready to introduce mechanical energy. So we have learned kinetic energy. We have learned the gravitational potential energy. And this is elastic potential energy. Let's put a spring S here, elastic potential energy. Now potential energy only can exist if you have a conservative force. And as we said, we're going to learn two conservative forces. Gravity, so you have gravitational potential energy. You have spring force, you have, well, elastic potential energy. We probably are not going to learn this one this semester. Thermal energy, chemical energy, nuclear energy. That's for our maybe physics 2. Now on the surface of Earth, you can define gravitational potential energy to be mgh. Because mg is uniform, so it's easy for you to do an integration. Basically, you are doing an integration of constant, so you get mgh. And for gravitational potential energy, there is a reference point where you choose it to be 0. And that is not very important, because for gravitational potential energy, what really matters is the difference, the height difference between initial position and final position. And this difference won't change no matter you choose here to be a 0, here to be a 0, here to be a 0. But to make things simple, usually in the laboratory we choose the ground to be 0, and people also sometimes use sea level or at 0, but as I said, where you set the potential energy to be 0 doesn't matter. Gravitational potential is mgh. What really matters is your final height, the initial height, and this doesn't change no matter where you choose to be a 0, to be your ground zero. Okay. And why we call it the potential? Because it has potential to do work. For example, if you put a rock on a hill, what happens if the rock fall down the rock? It will have a lot of kinetic energy in it after it go to the bottom of the hill, right? That's why we call it potential energy. And we can use it. Hoover Dam generate 4 million kilowatts hours of power per year, which probably is more than enough for all residents in maybe Cobb County, not Fulton County, for a year. So where does this energy coming from? Just imagine. See, you have a lot of water here, and they are raised very high. But here you have water, but it's low. So water from here, if you say you're just standing on top of this dam, you hold a big basket, you pour water down. Now, what kind of quantity of the water will decrease? Gravitational potential energy from here to here, right? And if you pour the water down, the initial velocity of the water on top of the dam is 0. What's happening to velocity of the water here? It's huge, right? So which means the water gets some kinetic energy. Where is it coming from? Gravitational potential energy when the water is high. So water fall from top of the dam to the bottom of the dam. Now the water initially is almost at rest, and then it accelerates to 80 miles per hour, faster than we are driving on highway. And then this water will pour into turbines, and the turbines will rotate and generate some generators to generate electricity. And after the water leaves this turbines, its velocity is only 10 miles per hour. So there is a huge difference. Very fast water becomes very slow moving water. Where the energy goes, it transforms into electricity. So is gravitational potential energy of water here becomes kinetic energy, very high kinetic energy, and kinetic energy becomes electric energy. That's how it works. Okay, it's good time for us to stop, and we'll come back for part 3.